I've talked about MAC bands as an example of some low-level wiring that helps us perceive the world. Now, another nice example is if you ask a very simple question, and it's just how do we actually perceive depth in the world? And this may seem like, trivial at first, but if you really think about it, we've already talked about how light falls on the back of your eyeballs on sort of a two-dimensional sheet, almost like a piece of paper, right? The retina is a two-dimensional shape, and somehow that two-dimensional shape then converts the light that falls on your eyeballs into these neural firings, and then in the back of your brain, somehow this gets built up and created into a three-dimensional image again, so that objects that are closer to you, objects that are farther away, and so forth. So the third dimension, depth, is actually lost for a while. And then nonetheless, of course, we perceive depth in all sorts of ways. I mean, it's possible to know whether a car is 10 feet away or 50 feet away, fortunately, right? If we couldn't do that, we would not be able to drive. So how is that possible? Well, there's a couple of different cues that help us with perception of depth. And some of them we actually get even if you just use one eye. One, mono, is a word, monocular, for just cues you get, depth cues that you can get even when you close one eye. There are also some cues we get for depth perception that are based on the fact that we have two eyes. These are called binocular cues, right? Bi, two. And then there are some cues that come from the movement of our eye muscles, and those are called oculomotor cues, which apparently PowerPoint doesn't know that word. So let's talk about each of those. And we'll start with monocular cues. One monocular cue is called linear perspective. And you see it on these train tracks here. You're literally looking at a two-dimensional image. It's a picture. It's completely flat. But nonetheless, you perceive depth. And if you want, you can actually close one eye. Just close one eye for a second and put your finger or your hand over it. And you'll still see the same amount of depth. Linear perspective in this image helps with that, because what you see is that these two lines, the train tracks, that we know to be parallel, the farther they go in the distance, the closer apart they are on your actual eyeball. Right? So the lines on the top of that image over here are actually just as far apart as these are over here from each other, but because they're so far away, this amount of distance over here looks a lot smaller. So that kind of linear perspective actually creates the perception of depth, and it helps us judge how big things are, right? We kind of correct automatically. We know, if something appears smaller over here than it does over here, it's in part because it's farther away, and we kind of adjust the size relative to these bars over here and not to the bars over here. So linear perspective is one cue that you get from just one eye, a monocular cue that helps with depth perception. Related to that is the cue of texture. Objects have a certain texture. Some are soft, some are smooth, some are rough, and so forth. If you see an object, the exact same object, farther in the distance versus closer to your eyeball, the closer it is, the more fine-grained information about texture you get. Just think about, for example, if you're walking on a cobblestone street in Philadelphia and you look at a cobblestone near you, you see every last bit of chewing gum, spit, also just rough edges of the stone itself. You get pretty enhanced detail because it's close to you. So there's a lot of texture information for things that are close. If you look at cobblestones far away, you don't get that level of texture detail. So your brain, your mind somehow knows that depending on how much texture is coming in, this gives me some cue about how far away something is. So that helps with depth perception as well. Third, there is this thing called interposition or occlusion. Those are two fancy words to just say something that's closer to something else, or closer to you relative to something else, will actually occlude some of that object. So if you look at these two squares, assuming that the blue one is a square, that's actually interesting in and of itself, that our visual system assumes for this to be a square. We assume automatically that this red square is closer to us than the blue square is, and the blue square is further in the background. And actually what's interesting about that too is that this is such a strong cue we pick up, occlusion and interposition, that if you look at this image, I bet you that most of you guys are seeing a white square here in the middle that's not actually there. Unless you've been playing a lot of Pac-Man, then you might actually be seeing 4 Pac-Man figures. But interestingly enough, we are so sort of, the system is so used to occlusion as a cue for depth that we will perceive a white square in front of 4 circles almost automatically. So you get these illusory contours in this case. You get a contour of something that's not even necessarily there. So occlusion, that's not a cue. Things that are closer to you occlude objects that are farther away. Then we have motion parallax. And this is about how quickly objects that are moving change position on your retina. And if you think about this, if you look at a car that's moving very close to you, right? It drives right by you. It falls on your eyeball, and then it goes very quickly from the left side of your eyeball to the right side of your eyeball, if it's going from left to right. And the closer it is, the farther, the bigger that displacement is in your eyeball. If you see the exact same car driving with the exact same speed, but now it's at a distance away, that displacement on your eyeball is much smaller. So think of, when you see a train in the distance, when you see a plane in the distance, a plane moves relatively little if you see it up in the sky. Of course, it's going a much higher speed, but if the plane were very close to you, not up in the sky, the displacement over your retina will be much larger. So depending on how quickly something changes location on your eyeball tells you something about how close that object is moving relative to your body. So motion parallax is another one. This too you can get by closing one eye. It's a monocular clue to depth. As I said, not all depth cues are monocular. Some of them also come into play because of the fact that we have 2 eyeballs. And these are called binocular cues. And one of these is called stereopsis. Now, the deal here is, this sounds much more complicated than it needs to be. The deal here is that you have 2 eyeballs, and these eyeballs are not exactly in the same location. One is more to the left, one is more to the right. If you now take an object and hold it in front of you and close one eye at a time, you'll actually see that the image of that object, in my case I'm now holding up our textbook, the image on the eyeball actually changes slightly because of our eyes being in slightly different positions. So in other words, each retina gets an image, and there's a disparity between these 2 images because of the fact that our eyes are not in the same place. We're not cyclops, right? So retinal disparities give the brain a cue of how far away something is. Why is that? Well, if you try with the object that you picked, just grab any object you can see, and you first hold it close to you. If you now close one eye at a time, you see that actually the image for each eye is pretty different because there's a large retinal disparity if something is close by. On the other hand, if you stretch out your arm as far as you can, and now you close one eye at a time, the image each retina is getting is much more similar. So what the brain does is it takes that input and then automatically calculates, if you will, the difference between the 2 retinas, and the more of a difference there is, the closer by something has to be towards your body. So stereopsis is another word for this. Just means that there's 2 eyeballs that give you a different image. So that's one binocular cue. There are 2 cues that are in some ways related to this, but they're oculomotor cues because they come purely from the amount of muscle tension and the rotation of your eyeballs. First of all, convergence. Convergence is pretty easy. If you just stick out your hand and hold up your finger, and then start moving your finger towards your nose, you'll see that when it's very close up, you're basically like you're cross-eyed, right? Your eyeballs are completely rotated inwards. So from the amount of inward rotation, your brain, quote unquote, knows how close up you're looking to something. The more inward rotation or convergence, the more close something is that you're focusing on. So the inward rotation of the eyeball or convergence, the amount of that gives you an idea of how far you're looking. Second, accommodation of the eye muscles, right? Whether you're tensing up these muscles or relaxing these muscles, make that you're focusing your lens to either be focused on far distances or nearby distances. So the brain again gets information from these eye muscles, and from that it can actually figure out whether it's focusing in on something that's close by or something that's far away. So 3 types of cues again: monocular cues that you get based on just one eye alone, binocular cues that you get from the differences in the images on your 2 eyeballs, and then some oculomotor cues that are due to the actual movement of the eyes. Now what's interesting too is that when we perceive, we also make a couple of, if you want, top-down assumptions about things. And one of those assumptions is called size constancy. From having been around the world, we assume that if things move closer to us, even though they become a larger image on our retina, it doesn't mean that they're growing in size. It just means that they get closer to us. And you can see this in this image. It's quite funny. You see this guy here, and you see actually the exact same guy over here. And if you measure it out, this image right here is the exact same size as the guy back here. So this is about 1.5 inches, I guess, and this is about 1.5 inches. However, I'm pretty sure that most of you see this as a very, very little person, because this guy close up, of course, has, quote unquote, grown in size, but we assume that this person has a constant size. It's just a normal person, just like this person is. And because of that, this person right here, we now assume to be close up. And because he didn't increase in size, we have to assume that this must just be a really, really tiny person, right? So what gives rise to this is size constancy. Fortunately, it's not like, when your friend is walking up to you, you think he's all of a sudden turning into an enormous giant and you should go hide behind a bookshelf in order to not get beaten, right? We assume that objects have a stable size, their size is constant, and as they move through space, or if you move through space, it's not that objects and people change size, it's just that your positioning in the world relative to these objects is changing. So that's one way in which our system actually top-down makes the assumption that things are constant. You can actually show that you can really mess with this, and one demonstration of that is called the Ames room. And rather than walking through this, I will post a video where you can actually see how this works.